In this video, we are going to prove the chain rule. And so as a reminder of what the chain rule says, it says if g is differentiable at x and f is differentiable at g of x, then the composition function capital F of x equals f composed with g of x is differentiable at x with its derivative being f prime of g of x times g prime of x. And so we want to show that this is actually true. And to do so, we're going to first make the following observation. So if y equals little f of x, and we're just taking any function f of x here, then if delta x is our change in x, we have that delta y is equal to f of a plus delta x minus f of a. So now this is something we've seen before. It's just saying that if we're changing our value of x from a by some value delta x, then our change in y is just the difference in f at the point a plus delta x minus f of a. And so recall that one of the definitions of the derivative is the limit as delta x goes to 0 of delta y divided by delta x. And this is f prime at a. And so that's just a definition of the derivative that we have talked about before. So there's nothing specifically new about that. So where we're going to make things a little bit different is we're going to let epsilon be equal to delta y divided by delta x minus f prime of a. So delta y over delta x is some value. We don't know what it is, but it's some value. You poke delta x and you can find what delta y is. We can compute delta y over delta x. And then we're going to just subtract off the derivative of f at a. So this is assuming the function f is differentiable at a. And so what we then have is that if we take the limit as delta x goes to 0 of epsilon, this is the limit as delta x goes to 0 of delta y over delta x minus f prime of a, which we can rewrite this using limit properties as limit as x goes to 0 of delta y over delta x minus the limit as delta x goes to 0 of f prime of a. Now, we already said that the limit as delta x goes to 0 of delta y over delta x is just f prime of a. So this is f prime of a minus f prime of a is a constant. That's the derivative at a point, so it's still f prime of a. So we get 0. So in other words, as delta x goes to 0, epsilon goes to 0 as well. Okay, so we've defined this function epsilon that has the property that as delta x goes to 0, it also goes to 0. But what we're going to do is we're going to rewrite our expression for epsilon in a different way. And so we have epsilon is equal to delta y over delta x minus f prime of a. But what we're going to do is we're going to solve for delta y. And so we're going to multiply everything by delta x. So we have delta x epsilon equals delta y minus delta x f prime of a. And remember, we're solving for delta y, so just adding the delta x f prime of a to the other side, we get delta y equals delta x f prime of a plus delta x epsilon, which equals delta x times f prime of a plus epsilon, where epsilon goes to 0 as delta x goes to 0. So now this might seem like kind of a random thing that we're doing here, but we're going to use this fact that we just found to actually prove the chain rule. So all of that was just to justify this equation, and we're going to use that now to prove the chain rule. So at this point, we are now ready to prove the chain rule. So we're going to suppose u equals g of x is differentiable at a, and y equals f of u. So y is really f of g of x. I'm just plugging g of x in to the function f of x, but I'm writing it as f of u just for notational purposes. And this is differentiable at b, which equals g of a. So now what we're going to do is we're going to try to take the derivative of y, in a sense. We want to find dy over dx, so we're going to look for delta y over delta x to start with. And so what we're going to do first is we're going to use our increment argument on both the change in u and the change in y. So our change in u, using just the argument we did above, is going to be delta x times g prime of a plus some epsilon 1. And we're just writing it as epsilon 1 because we're going to have two of these. And then this is where epsilon 1 will go to 0 as delta x goes to 0. So that's just using exactly what we did before. So this argument we did with the delta y, we're just applying it to g. Similarly, we can do the same argument with y equals f of u. And so we'll have delta y equals, this time it's going to be delta u because y is dependent on u. So we have delta y, then f prime of b plus an epsilon 2, where epsilon 2 will go to 0 as delta u goes to 0. So now remember, we care about delta y over delta x, and so we're going to rewrite delta y in terms of delta x. And all we're going to do that is we know what delta u is, that's why we found delta u, so we're just going to plug that in. So we have delta y equals, I'm going to rewrite this in the other order, f prime of b plus epsilon 2 times delta u, but delta u we have above. So this is f prime of b plus epsilon 2 times delta u, but delta u is g prime of a plus epsilon 1 times delta x. So I just replaced delta u with what it was equal to. And now one thing to note is that as delta x goes to 0, delta u goes to 0. And that's sort of easy to see here, as this expression right here is just some number, and we're multiplying it by something going to 0. So we're going to have some value times something getting really small, so that whole thing goes to 0. So as delta x goes to 0, delta u will go to 0 as well. And so now we want delta y over delta x, because we're going to take the limit of that, that's the definition of the derivative. So just dividing everything by delta x, we have delta y over delta x is equal to f prime of b plus epsilon 2 times g prime of a plus epsilon 1. And now we want the derivative, so we're going to take the limit as delta x goes to 0. So dy over dx equals the limit as delta x goes to 0 of delta y over delta x, which equals the limit as delta x goes to 0 of g prime of b plus epsilon 2 times g prime of a plus epsilon 1. But now recall that epsilon 1 goes to 0 as delta x goes to 0. That was a fact that we knew. And as delta x goes to 0, delta u goes to 0, and epsilon 2 goes to 0 as delta u goes to 0. So epsilon 1 and epsilon 2 just go away in the limits, and f prime of b and g prime of a are constants, and so we end up with dy over dx just equals f prime of b times g prime of a. But b, remember, is just g of a, so this is f prime of g of a times g prime of a. And that's the chain rule. And so what we just found there is the derivative of the derivative of y with respect to x, It's just f prime of g of x times g prime of x. And so that proves the chain rule. So this is a bit complicated of an argument, but I just wanted to give the justification of the chain rule here. Just remembering the chain rule is usually sufficient for a Calculus 1 class.